All right, folks, a very warm welcome to Support Vectors meetup group and our weekly paper reading session. The topic today that has been proposed by some of you was GEPA. This is actually a paper that came out a little while ago in July and August. So it's been a couple of weeks, but it did have quite a bit of impact. And so I think it's a great paper choice. GEPA, reflective prompt evolution, can outperform reinforcement learning. The title itself contains the main thesis. What they are saying is there are things you can do with the prompts that make the LLM produce results superior to what you would get if you took the LLM through a reinforcement learning exercise. The authors of the paper are quite well-known places and authors. Lakshay Agarwal is a graduate student, I believe a PhD person at Berkeley. You may recognize quite a few big names. Christopher Pott is there. There is Matai Zaharia at Stanford and Omar Khattab, also his student Omar Khattab, also at Stanford. The paper is from UC Berkeley, Stanford, Bespoke Labs, CI, Notre Dame, Databricks, MIT. That's a pretty powerhouse. Quite a few powerhouses are involved in this paper. Now, this paper is long and somewhat dense, and I would like us to have take a two-phase approach to it. I'm going to talk a little bit about it, unpack it, and then I'd like to open it up for discussion. But as I discuss this paper, I very much invite you all to keep interrupting me and asking questions or putting in your suggestions. It is likely to be much more fun if we all go through interactive process. So before, I'd like to give you some background. This paper mentions things like, right off the thing, GRPO, and then it is talking about something called genetic Pareto, which is what they are suggesting. GEPA stands for genetic Pareto. So we need to know what is a Pareto frontier for a bit of a background. And more specifically, what is it exactly that they claim, or the task that they claim that GEPA can do better than doing reinforcement learning? How do these things come together? Right? And GEPA also outperforms what was currently a pretty good prompt optimizer, MIPRO. And so the whole question is, what is a prompt optimizer? I will talk about and give a bit of a background for all of these. Now, before I do that, I want to make sure that you guys are not already very well versed with these. So just as a show of hands, guys, how many of you would like me to explain a little bit about what is reinforcement learning? A very quick way. Since I didn't see any show of hands, can I assume that all of us know about reinforcement learning?
Basic will be great.
Basic, okay, I'll do that. And let me ask the converse question. How many of you know what a GRPO is? Any show of hands?
I know.
You know, okay, wonderful. One person knows. So maybe a little bit about GRPO. How many of you know about evolutionary algorithms or genetic algorithms? No, so we'll talk a little bit about that. And do we know, how many of you know what a Pareto efficient frontier is, or what Pareto refers to? None. Okay, so I'll talk about that too. How many of you know what is MIPRO V2? None. So that also I'll take as a no. So I will talk about it. And guys, if you all know, do speak up, because we can save time and rush forward. This is a very interesting, dense, and long paper. How many of you know what is prompt optimizer? Okay, Saurabh knows prompt optimizer. So one person, Vinu knows prompt optimizer. So that is excellent.
I just know at the high level.
Okay. All right, so we'll talk about it today. So I will assume, in view of the background, I'll sort of assume a basic, a baseline that starts from 0. So, and then we'll move quickly. If you guys feel we know this stuff, let me know and I will move quickly through this. See, when you have a task, given a task, oh, this is too fat. Given a task, T, or you can also think of it as objective, task T, you want to use a model. We want to, let's say that for that task, you give it an input X to the model M, and you get a Y hat. You can judge for the task like this. You can judge how good the model is using some metric. So, for example, if you're doing search, you could use recall precision at K, you could use MRR map, NDCG, area under the precision recall curve, etc., etc. And quantify imperfection with loss function. So this is 101. Right? So loss function will be some function of y hat. The loss function with the loss function that is differentiable, right? Now what happens is that when you do have a loss in a model is made up of parameters theta. Now every theta I is responsible for the loss, is partially responsible for the loss. So what it will ask is, what can I do? How can I change to make the loss go away or decrease as far as I'm concerned? And the way you do that is you look at the sensitivity of the loss with respect to that particular parameter. This, and more formally, you write it for all the thetas as the gradient of the loss. And what you do is you backpropagate the gradient through the entire model and so forth. But at the end of it, you have the learning step in which you say theta is equal to theta I, or theta beta, let us say, is theta I minus some learning rate scheduler, which is a function of how many epochs you have gone through, times some function of momentum and the gradient, right? Some function of the gradient of theta of the loss, right? Or specifically, because we are talking about one particular theta I, theta I. So this would be your gradient descent equation, gradient descent equation. Now, whenever you talk about a gradient descent equation, in the simplest form, the G is just the gradient itself, but then there are much more sophisticated ways of doing it. All these G's are called optimizers. This is again to pick. These G's are called optimizers, right? And optimizers for gradient learning. What is the purpose of it? So now let's think about what an optimizer does. It helps the parameter get better, little bit better at each epoch. In each mini batch of learning, the parameter gets a bit better, right? And so that's the job. It optimizes the parameter. And by optimizing the parameter, it optimizes the model to produce better results. That's the point, isn't it? Now, in the case of a large language model, so now we go to the case of our LLM. We have an extra degree of freedom. In an LLM, what happens is you have a model, LLM, model M, which is made up of theta. It produces an output, y hat, let's say. right? And I'm taking a full answer. You can take it the next token, but you can let us be a little bit more coarse-grained and say the whole input goes in. Let's say that a user input, what you call a user prompt, goes in. But then to steer the prompt, you often put a so-called prompt instruction or system prompt. Prompt instruction or system. You put a system prompt here, right? Let me represent the system prompt with the parameters I. Right? I think this paper uses something else. Let me align with the paper's notation. What does the paper use? It uses argmax, xman, theta. Okay, it uses something which pi. It uses pi, right? But I won't use pi. I'll use, okay, maybe I should use pi itself. Pi. It uses pi parameter. Is the prompt, is a system prompt. So now we know basic prompt engineering is associated with the fact that by changing the prompt instruction or the system prompt for the same user input, you get a different answer. Because what goes into the LLM is the union of this. So in other words, X, if you look at it as this, X, and here's the model, this is theta, and a y hat comes out, then X is the union of two things. X is the union of, X is equal to a pi, which is the sys prompt, union, right? Union, or if it helps you, just think of it as a concatenation and user input. Do we agree with that? And to the extent the LLM is a function of the input, therefore, these act as steering. They act as rudders or steerers. Rudder or steering vectors, steering tokens. And these tokens become vectors because what really goes into the large language model are vectors, and so you get steering vectors. So therefore, if you look at the model as a function, you can say that the output is basically a function that the model produces out of two things. It produces a model out of x. So given x, function of x, given pi, and given the parameters of the model, right? It depends, the quality of the answer that you get, output, user input. This is the sys prompt. This is the model parameter. And this equation is actually central to understanding this paper. Do we agree, guys, that this is it? And so if you want to make the model produce an answer that is better and better, we have, therefore, we have two ways to steer it towards the better answer, two ways to optimize. The model. One, parameter optimization, theta. You make better theta, right? Parameter optimization through fine tuning. And the second thing that you can do to an LLM is make prompt better, make sys prompt better. I hope this is something that we are all familiar with. We do that. Now the question is, this question has always remained. Can we, and we do that, we use whatever LLM that we use. Our tendency is to first create a better prompt. There are all these templates like CoStar and whatnot. Everybody has their favorite template that helps them write a better prompt. So we will focus on the second part. This part is fine tuning. So this is fine tuning. But this journey breaks up into two parts. One is prompt engineering, And there's another set of techniques which is called prompt optimization. And the two differ. Prompt engineering is done by humans. Somebody sits there and says, you know what, let me change the wordings. We all do that to get a better response. If you are given, for example, a task like extract data from this page, we all sit and carefully write a prompt to extract data from the image of a page, right? JPEG of a page. Then that is prompt engineering by human. And then there is another effort called prompt optimization, which is a machine taking your prompt and making it better. Why would you want to do that? See, what happens is that for a given task, you can have many models, model MI, version J, right? You might say, will I use Quen or would I use Minimax? Will I use OSS, GPT OSS? Will I use this, Llama, whatever it is? It's a choice of model. And a model and will have a version. The trouble is, if you start hand optimizing prompts, then you will end up with a situation that every MI, VJ, tuple will correspond to a perfect prompt, IJ. Let me call that you will be, let us say that by hand engineering, by careful experimentation, by trial and error, you can find the perfect prompt. In reality, you don't find the perfect prompt, you end up finding something good enough. Right? And then you stopped. But this is still insanity. You put a lot of effort putting a prompt together. And then actually there is a hidden variable that is even more annoying, which is hiding like a ghost in this. Compute budget. Compute budget at time t. What it means is that if you're using a frontier model, the frontier model may, when you invoke it over a API, it may decide how much compute to allocate to your request. Right? And as many people have observed, when a new version of a model comes, the previous versions they begin to sometimes, there's anecdotal evidence that they tend to not perform so well. Right? And why is that? It's not a malicious thing. It's just that the company has finite hardware resources and it is reallocating those resources for the latest and greatest model. So the compute resources available to your older version of the model begins to go down. So you're hostage to that. The same prompt, which for the same model and the same version was working well today, tomorrow might not work so well. If you're using a frontier model, if you're making calls over the and paying by the tokens, right? Which is, I suppose, an argument in favor of having local models totally under your control. But it is what it is. So that makes for a very complicated situation. And so prompt ops, managing prompts for different models and different versions, has become a subfield of its own. And it's quite insane. And so the question worth asking is, can we do this? Create one good prompt. Let's say that prompt engineer steps are: one, prompt engineer, the best hand prompt you can do, or just be good enough, can do for a model, for a model MI version J. And then what you do is you give it to a machine as a starting place, and ask it to dynamically make it better. Right? So now the whole question is, well, how in the world is it going to make it better? Right? What it does is, some of the early efforts were like this. A language has a lot of nuances to it. So what it would do is it would start making the machine. These things are called prompt optimizers. This is called prompt optimizer, and these are prompt optimizers. What they do is they make perturbative changes. Perturbative changes like small changes to the prompt. And by prompt, I'll always mean system prompt. I don't want to keep repeating the word prompt, system prompt all over again. So I'll just say system prompt or prompt instruction. So they will just change a word slightly, the phrasing, or replace it with a synonym, or do things like that, or add a little bit, one more sentence to the prompt, right, to clarify its meaning. So what will happen is the machine will go through a sequence. Pi0 goes to pi1 to pi2, and at each point it will check, is it doing a little bit better? You can give it a gold output, right? It becomes a form of supervised learning. You give it that, given this input, this is what the perfect answer should look like. And now the machine will say, okay, if this is the input, this is the output, I can't change my parameters. But what I can do is I can discover the best pi, the best system prompt. So it will start making little changes that gradually take it in the direction of a better and better output, or makes it closer towards the goal output. This is prompt optimization. Now, there's quite a bit of theory on how you do that. The main problem with prompt optimizers is this. While parameter optimization benefits from a differentiable space, see, when you do, let's look at this. When you do parameter optimization in a model, when you fine tune a model, it's actually in some sense easier because you can get the gradient of the loss. And because you have the gradient of the loss, you can therefore flow towards a better, in a very guided way, right? It's a gradient descent process. On the other hand, in a textual landscape, in a linguistic landscape of words, there is no gradient. It is a non-differentiable discrete space. Do you see that, guys? You're dealing with a non-differentiable discrete space. That makes it very hard. Gradient descent goes out of the window right away. Nevertheless, people have found out many, many ways of doing it. So instead of going through, so you can start with very basic ways of just making small changes, few little changes here and there, and see what happens, and keep doing that till you gradually drift, zigzag your way towards a better prompt, right? That is one. But then there are two, like one, the gold standard so far was something called MIPRO. By the way, an open source library that does this very, very well is DSPY. A DSPY is nothing but a library of prompt optimizers to a large extent. Right? And they have been pretty successful. Uh, they probably should be a lot more successful. Most people don't use DSPY because they find it a little hard to understand and use. But this is all there is to DSPY. It is a library for prompt optimization. Once you're done with your own handcrafted prompt, give it to DSPY and make it better. What are the advantages of doing that? One advantage is you got it right for one model. If you notice that the performance has gone down, all you have to do is rerun your DSPY, right? And it will discover another variant which is better. A new version comes out, it will adjust to that. A new model comes out. Now you can again go from this to that. You can keep on discovering the best model without hand engineering the model, right? It becomes the difference between hand building things and manufactured things, right? You don't need to hand build the prompts. So MIPRO, on the other hand, is a very powerful prompt optimizer, and for the longest time was a state of the art. And what it does is it uses something called Bayesian inference. And Bayesian inference is actually the best thing, the best that you can do when you don't have a differentiable space. Right? So what it does is it basically tries to guess in in this linguistic landscape, which direction to go to, right? And so it goes there, and then it asks, did it lead to improvement? But it keeps track of the direction you went. And if there is improvement, it just uses it and says, oh, that helped. Let's go a little bit more, right? And it tries to use the experience of past movements, and therefore the word Bayesian, on the evidence that it gathers, to come up with a posterior belief that what exactly should I do next, right? So it is a guided flow or guided process of discovery of the best prompt. Bayesian inference is pretty good, actually. It was the best till this paper came out this month. And this is it. So now with that background, I will come to this paper, which posits yet another prompt optimizer, which is remarkably effective. It's called GEPA. Now, before I go into this paper, I will just drop a caveat. See, we here at Support Vectors have been playing with GEPA for some time, and here is our experience. Despite what the paper says, I mean, this paper is a remarkable paper. It has achieved good results. Namely, but this paper might lead you to believe that it somehow makes reinforcement learning useless, right? Or GRPO useless. And unfortunately, that conclusion was arrived at by quite a few YouTube bloggers or YouTube channels. That is, in my view, a completely wrong understanding of the paper. It does not replace reinforcement learning. It does not replace GRPO in a broader sense. All it says is, in certain situations, you should first try prompt optimization before you do reinforcement learning, because prompt optimization is more compute efficient. It is more rollout efficient. Why not go the easier path first and see how much improvement you get? And if you don't do that, and let us say that the easier path would have taken you to quite a bit of improvement, you are sort of leaving. It's an opportunity cost. If you jump straight to fine tuning or reinforcement learning, you are taking a much harder path, a more rollout inefficient path to come to an answer or come to a model that you could have arrived at better, much more easily. And that is the way I would interpret the results of this paper. So I would say that I disagree with those many YouTube videos that I've seen that have read the paper and come to the conclusion that, oh, reinforcement learning is dead, fine tuning is dead, GEPA is the way to go. GEPA is a significant contribution, but nevertheless, it doesn't wipe out what is a long intellectual tradition. So with that, we now will come to GEPA and what is it that it proposes. But to explain what this paper proposes, we need two more concepts to understand. One, or rather just one concept. One is genetic algorithms or evolutionary algorithms. Evolutionary algos or genetic algos. These have been there for many years. For decades, it's been there. And I'll talk about this. The other is Pareto. We'll talk about that. So, evolutionary algorithm, the best way that I would say is, okay, let's say that you're trying to, well, the best way is you see it happen in nature. There was a very interesting, actually, experiment that I'm reminded of with dogs. As you know, most of you know, I absolutely adore dogs. Okay? So this was an experiment actually done. I believe it was a Russian scientist who did it, a biologist who did it. What he did is he took wolves and he lined up the wolves. And what he would do is he would send a kid near the wolf and see at what distance of closeness or what degree of closeness would the wolf become violent or aggressive or would start barking or pouncing or something like that. And so measured that distance and they looked for those wolves in the pack that were the least aggressive. In other words, they let the kid come as close as possible. Right? Now, wolves being wolves, they are pretty aggressive creatures. So you would imagine that even when the child is pretty far off, the wolf will get aggressive. And so what they did is they would take the least aggressive of the wolves from that generation of wolves, and they would now crossbreed them. They would have them have the next offsprings. Right? Now, as you know, with dogs and wolves, they reproduce pretty quickly. After 1 or 2 years, they are ready to reproduce. Right? And so this was a long-running experiment, and you can have many, many generations of wolves uh, in a human lifespan. What they observed in this experiment is that after many generations and by interbreeding, only the least aggressive wolves, what they found was something remarkable. The offsprings, after many generations, they looked uncannily like dogs. Their ears, instead of being pointy and aggressive, they started turning down. And they started developing a cute face. They started developing a white spot on their chest. And all the cuteness that we associate with dogs began to emerge in just a few generations. I often quote that example because that is, in effect, what you try to do in genetic algorithm. And then now I'll take the same experiment and try to recast it a little bit closer to home. Let's say that you want to forge the perfect, let's say, metal for a sword or for the hull of a ship or for some construction. You may start with people, normal people, and you may teach them whatever it is that you want to teach them. And then what you can do is you can check for people, you can let them evolve and check for people who have more inclination to be able to solve the problem better. In a few generations, you might find that the people who really solve the problem quite well, some of them have the traits of a physicist. They really are focused on the strength of material, the stress and strain, the physical properties of the material, which is very helpful in creating the perfect, let's say, some architecture with metal. Right? On the other hand, some people may have developed into chemists. They may understand the chemistry of the material. And as you know, a material, okay, that matters a lot. And the chemist can be very detail oriented and work with molecules and reactions and every single thing. Now, to really build a good architecture, you not only need to know the strength of structures and so forth, but also the strength of materials. And at some point, you would realize that if you have physicists and chemists, you can, I suppose, hybridize their mental knowledge into the next generation somehow and create a metallurgist. Right? Because a metallurgist or a material scientist is exactly that, is equally endowed with physics abilities as well as chemistry abilities, right? Understands uh, both aspects very well. So what you can do is you can keep on by crossbreeding, by interbreeding, or by creating successive generation in evolutionary algorithm, which additively takes the best of two parents to create a better version of it. That is the pursuit of evolutionary algorithms. That's what evolutionary algorithms do. So keep that in mind. Now there comes a question about Pareto. But anybody has heard the word Pareto? What does Pareto stand for? The most popular picture that people have of the Pareto's law or something like that. Anyone? Is there anyone still there in the remote audience? I don't know.
No, we are here. Asif, I'm here.
Yeah.
So this is Krishnan.
Yeah. Hi, Krishnan. So anybody would like to chime in on Pareto? What is Pareto?
Pareto, I don't know.
Pareto's principle.
Come again?
Pareto's principle.
What does that say?
20% of this one can get 80% of work done.
Work done and so forth. Yeah. Like the first 80% of the effort is easy. Results are easy to get. Last 20% are the hard ones, right? 80-20 rule, 90-10 rule. People have many variations of it. Right? and that the 80-20 rule would say that just a little bit of effort will get you, 20% of the effort will get you to 80% of the result. And then the rest 80% of the effort will go into getting you the last mile, the last 20% of the result. So that is the Pareto's principle. So I want to explicitly say that is not the Pareto's principle we are going to talk about. We are going to talk about a different Pareto's concept. It is called Pareto efficient frontier, or more simply, it is just called a Pareto frontier. Let me introduce the concept in a very simple way. So, kids being kids, this used to happen to me when I was a kid. I would go to a children's fair, right? Where they think of it as some sort of a circus or something like that. In the fair, I would have a small pocket money. Now, with the pocket money, I could buy candies. I had a choice of candies. I could buy lots of cheap candy, standard candies, or I could buy more expensive candies, tastier, more expensive candies. But now they would not be as many that I could buy. So what would happen is, let's say that the price, the taste, so let me just say price or quality. And let's say that the price and quality are directly related, and there is a quantity. So what would happen is the relationship is like this, right? At any given moment, let's say that I have bought this quantity. Let me call this place A. This quantity and this quality of product. Let's say that this is the coordinates are A and B, right? And A and B are the coordinates. This is A and this is B. So I have A quantity of B quality candies. And suppose I have budget, I can buy more. I have two directions to navigate. I can keep going and increasing the quantity till I run out of my pocket money, right? So this is one direction I can go, or I could go in this direction and keep the quality the same and acquire a lot of candies. Does that make sense, guys? But ultimately, I would hit a wall, right? This wall that I hit is the literal budget that's putting a constraint. So I would say that common sense says that if I really love candies, whatever I do, it should be a point on this curve, isn't it? I would have used up all my pocket money to get candies. Guys, does it make sense? This wall is called the Pareto efficient or Pareto frontier. Because all the points along this represent a limiting situation. Whereas if you are at the point, X, you still have ways to go. You still have money left to either optimize, right? Either get more quantities or get a better quality product. Right? So what happens typically is based on our inclination, we slide back and forth along the Pareto frontier somewhere and find based on our taste, based on our inclination, we land somewhere on the Pareto frontier with the candies. So with that example, the thing to note here is, and we are pretty much done with the preliminaries to answer this question. So the thing is, given multiple objectives, what are the objectives here? Want more candies and want tastier candies. Both of these are objectives, but when you hit the Pareto frontier, you cannot increase one without losing out on the other, right? So for example, let us say that you are at P and you want to increase the quantity. You can do that by going to Q. But when you go to Q, you lose quality, isn't it? If you go to R or S, you keep losing quality. So you are on the Pareto frontier if you try, and you know that you're on the Pareto frontier, when any effort to improve one objective leads you to degrade on the other objective. That's the definition of a Pareto frontier, right? So with all of that background, we are ready now to understand this paper. And before getting too much into the technical details of the paper, let me give you the gist of the idea of this paper. See, people have been fine-tuning models for quite some time. As I said, you can fine-tune the model or you can prompt optimize, right? And what this paper says is something that actually is, from a practical perspective, it's common sense. If you remember, those of you who take my boot camps, I always keep saying that your escalation ladder should be one, prompt engineering, right? Prompt engineering. Two, prompt optimization. Make it. Right? And third, see if you can drag it. Just sneak and drag and do it. Sidecar, any sidecar method. Right? Or some auxiliary model or something else you can sidecar in. Right? And last of it should be fine-tuning. And in fine-tuning also, you can do SFT first and then try RL, because RL is hard, right? So it is an escalation ladder. Most of you are familiar that I keep advocating this escalation ladder.
So
That you should always follow this escalation ladder. Yeah, go ahead.
I said one question. Okay, so think about the first two options, prompt engineering, prompt optimization. So they don't help the next prompt, do they? I mean, compared to RAG or fine tuning, I mean, it does not do anything to help the next prompt that comes.
Absolutely right. So remember that all the escalation ladder that we have mentioned is specific to a task specific. And so even when you fine tune a model sometimes, quite often, for a specific task to do with. Hamad, go ahead.
I was going to ask, I don't know if the microphone is on.
They should be on, actually. If the battery is off, take another one.
Oh, no, I'm not on the Zoom. That's the problem.
No, you don't have to be on the Zoom. You can speak into the microphone. Yeah.
My question was similar to, is the whole point of GEPA or GEPA what's it called, one shot?
No. GEPA is slightly different. We'll come to that.
Okay.
Right? But yes, see, whenever you go to your point, Sanjeev, RAG, when you get away with RAG, there is a generality to it. You're basically saying, I'll bring knowledge that will help the LLM answer the question. That certainly helps. Any kind of sidecar like that definitely helps. Or tools. For example, you agentify it. You bring tools into the game, right? All of those things amplify the effectiveness of an LLM and definitely help. And there is a generality to it. But here we are speaking about optimizing it for a specific task, right? Like with very clear objectives. Like, for example, suppose you want to do, given a text, you have multiple objectives. Tell, does it actually answer the question? And how well does it answer the question? One. Two, how good is the diction? Right? How poetic or how well articulated is the explanation? The second objective. Right? So, for example, you may have very well answered the question in the most boring way possible or the most confusing way possible. So the clarity of the exposition is a second objective. The third objective, for example, could be that given, and so for example, if you're dealing with an email or something, or let's say that there's a question or there's a topic of essay, it could be, are you arguing, which of the lines of argument you're taking? Are you taking for, against, Or it could be like, are you taking it, many approaches to debate it, which of the approaches. So now what happens is you are asking an LLM to correctly identify multiple characteristics in the text. How well it aligns with the question or the topic of the essay. How good is the language and clarity, right? Maybe just basic things, how many grammatical mistakes there are. And finally, what is the line it's taking, for or against. Some topics are easier to argue for than against, right? And so you again end up with a multi-objective situation, isn't it? And typically, these are the situations that LLMs struggle with. If you think about it, you do structured data, return value in very practical terms to the LLM. You'll say, okay, give me data in my structure. You have a pydantic base model in which there'll be 4 separate fields, each of them to be individually populated. The LLM is trying to do that, right? And usually when you deal with that, think about it like that. Bringing more knowledge may or may not help you. RAG will not help you at that situation, Sanjeev, isn't it? And therefore, the choices that you're left with is you can either fine-tune your model to better be able to discern those properties. And if you try to fine-tune, you'll have to give lots of examples. Or you can try to discover a better prompt. Is that meaning coming across, Sanjeev?
Yeah, I think so.
Yeah. So that's the sort of situation we are looking at. Now, given this escalation ladder, actually, and I feel that this is important because this is how in practice you should move, because it ends a lot of unnecessary debate, which never happened when you actually build something, but happens when you do pie in the sky debates. Right? And you see a lot of that, especially associated sometimes with this paper. So the escalation ladder, given that, now let's look at fine tuning. So what we will do is this paper argues, and not because I don't believe in fine tuning, but I'll just mention what it is trying to say. See, in fine tuning, what happens? You treat the LLM, you give it an input, you get an output, right? So you compute a loss here. So in supervised fine tuning, you know what the perfect Y should be. Ground truth is known. Isn't it? You know the Y label that should be there. Therefore, you can compute the loss, and then you can take the gradient of the loss and work with the gradient, and you can improve the model. That's the whole story of supervised fine-tuning. Now, if you're doing a reinforcement learning, RL fine-tuning, let's say GRPO, what do you do? What you do is the model X goes in, the model produces a Y hat. You have no. Okay, yeah, guys, give me a moment. Yeah? Was there something? Oh, might have been showing one now, but oh my god. Yeah, maybe. Okay. Sorry, something scared my dog. So you have a reward function that you tell how good the answer was. It is a reward function. And in GRPO, what you do is you generate lots of rewards, and you take the best reward, like your relative reward. But in any case, whether you do GRPO or you do, whether you do supervised fine-tuning or RL, FT, fine-tuning, in both the cases, what you are left with is just a number. If you think about it, whether it's a reward or it's a loss, the loss is a number, isn't it? it is a number, scalar value that you're computing. And signal is a scalar value. And it is learning from that scalar value and trying to figure out, what can I do to make it better? How can the model produce a better answer? So and that brings us to the main thesis of this paper. This paper says that, see, language models are good at what? They're good at language itself, isn't it? And so let's do, and this is a core idea of the paper, it says, let's do this. We will take and we'll give it an input and some prompt, and we will let it reason through. We will look at the trace of its answer. Right? So what will happen is, if you look at when you invoke an LLM with its prompt X, which is made up of user input and some sys prompt. Let me write the sys prompt as Y. Actually, pi goes into the LLM. What does the LLM produce? It not only produces a final answer, it produces a trace of reasoning. Isn't it? It says, I did this, therefore this is the answer. Right? So what we can do is we can give it a gold standard answer, good target answer. And then we can say, see, you produce this answer, but you should have produced this, right? You show the Y hat and you say, this is what we wanted. Let's say target. And then you reflect on your thinking chain, or figure out where things went wrong, right? What you should have done to produce a better answer. So LLM will start thinking, right? And it will say, you know what, in view of the fact that my answer was not so good, maybe I need to change it a little bit. But when it tries to do that, remember, what will it be forced to change? It will reflect upon its own and it will say, you know what, if I change the system prompt pi a little bit, then it will guide me towards the right answer. You're getting that, right? So it is the LLM reflecting on why it produced an answer based on the system prompt it had to work with. And then it would come up with a correction to the system prompt, a small correction to the system prompt. So you use the LLM itself to produce the system prompt to a better system prompt, and so forth. Does that make sense? And now that is the core idea, that you can making the LLM reflect upon its own traces of reasoning, because ultimately it's a language model and it thought it through in language. Why not? And that language trace is a very rich signal. It is not just a number. It has a lot in it that it can work with. Let it work with that and say, what do I now do to the trace or to the system prompt to make it better? So then what would happen is, let us say that, and now comes the genetic algorithm part of it. Now comes the GEPA part of it. GEPA, genetic algorithm. What it says is that produce a few good prompts. Let's say that you make a few variations of the prompt to see, okay, if I change this, will I get better? So you come up with some system prompts, right? And let us say that these two were really good, right? Or these two were really good. And intuitively, what you can do is you can use these to you have two choices at that moment that you can do. You can take one of the good ones. Let's say that the good ones are A, B, and C, right? You have the following choices. You can take A and you can mutate it, just make changes to it, and see if that makes it better, right? So that is a mutation approach. The alternative is you could take two good ones and sort of hybridize them. Take the best part of both and create a new prompt. So you can do a hybridization of, let's say, A and B. to create a new prompt. But in either case, there are two possible routes you can take to produce a better prompt, right? So you see the genetic approach to it. What you can now, what will happen is if you mutate it, if it is bad, you throw it away. If it is better, you add it to the candidate pool, right? Likewise for hybridization, if the hybridization is not as good, you throw it away. If the hybridization is good, then you keep it to the candidate pool. So what happens is generation after generation, you have a pool of this, you have a pool of this, you have a pool of this. You start getting a richer and richer pool of candidate prompts, isn't it, guys? You start getting better and better prompts. And you can decide when to stop, after how many iterations to just stop, right? That's your budget overall, because you need some stop criteria. You can't just go on doing it. You need some stop criteria. So that is the genetic part of it, generational, evolutionary part of it. What is the Pareto part of it? See, you only keep the candidates which in that generation are optimal. So one may be optimal for one of the objectives, another may be optimal for another of the objectives. Do you see that, right? So you keep a pool of things that are Pareto optimal, right? Or on the Pareto frontier. And therefore the name of the algorithm, genetic Pareto. So this is it. This is what this paper is. And I will just go, after you get this idea, the rest are results. So now we will read this paper and it will make a lot of sense to you and pretty obvious sense to you. Large language models are increasingly adopted to downstream tasks via reinforcement learning. Methods like GRPO, which often require thousands of rollouts to learn new tasks. In other words, to do RL, you have to do a lot of forward pass, reward, the whole trajectory, reward of the trajectory, then adjusting the weights, right? That's what you do, which often requires thousands of rollouts to learn new tasks. So the word rollout, by the way, is very reinforcement learning specific. In the case of supervised fine-tuning, it would just be a forward pass, back propagation, gradient descent, one rollout, right? We argue that the interpretable nature of language can often provide a much richer learning medium for LLMs compared with policy gradients derived from sparse scalar value. So now you know sparse scalar rewards. Why? Because they're just numbers. To test this, we introduced GEPA, genetic Pareto, a prompt optimizer that thoroughly incorporates natural language reflection to learn higher level rules from trial and error. Given any
Asif, can I ask you, sorry to interrupt. So I somehow thought GEPA is more like a DSPy optimizer, right? Something along that line. But now we are talking about GRPO, which is more of during the training time. I'm trying to reconcile that.
Good point. See, it is pointing out that it is not RL at all. It is a prompt optimizer. And what it is saying is that it is more rollout efficient in the sense that very quickly you converge to the best prompt, right? Good results.
Yeah.
Ultimately, goal is to solve the problem. Whereas when you use GRP or RL techniques, it takes hours and hours and hours to get there, right? That's what they're trying to say.
Okay.
So they're not saying that they are RL. They're saying they are the alternate approach to RL.
Okay, got that. Thank you.
So
Going back to Krishnan's question, does that mean we can use this as a replacement for DSPy as well?
no. This paper is literally from the DSPY guys. And now it is the latest and greatest optimizer in the DSPY arsenal.
Oh, so
So if
this will be like a replacement for
Wipro,
MIPRO, yeah.
And so in our team, we have been playing with it a lot. We do see, so here's the thing, for many situations, some situations it works very well. For some other situations, the improvements are slight. But there are a class of situations in which nothing but reinforcement learning works. That is our experience. Because this paper did generate quite a bit of controversy. So we have done quite a thorough set of experiments, digging into it and seeing what does it mean in real terms, in real tasks, enterprise, applicable tasks.
Is everything like semantic determination? Because like the LLM is choosing if the answer is wrong or not, and then it's
Yeah. So what you're doing is you're giving it a gold answer, and you have a LLM as judge, which basically is saying, okay, not quite yet, and then it's looking at its trace, and it's saying, okay, given the way I thought, what can we do to the system prompt? How can I amplify the system prompt or clarify it? Generally, what I notice is that it tends to write a longer, better system prompt with less ambiguity. Right? That's the way. Because see, when there's ambiguity in the system prompt, LLM doesn't know which way to go or what to make out of it. It'll make something out of it. But when the answer is wrong, what will it do? Maybe that's not what was meant. The answer is implying I should have taken this route. Right? And so then it goes and cleans up the system prompt so that that specific ambiguity is gone. Right? That's what we will see. So here is the benchmark that shows that actually this is important. Let me just dwell on this a little bit. This image a little bit. What it shows is number of rollouts. Do you see that on the x-axis is the number of rollouts? And to achieve a certain score, obviously they have taken a case in which it works really well for this GEPA, right? And hotspot QA is one of those examples where it works really well. So it shows that GRPO has saturated here, and it takes a long time for it to saturate here, right? Whereas if you look at this, GEPA achieves results in much less number of rollouts and a number of learning cycles. Likewise, you can say that here it gets there much faster, right? Which is the point it is making. Now remember that, see guys, this is also a case in which you bring out your best results forward. Or at least I had the slight feeling. It's a very beautiful result. Nevertheless, our experience is that for many cases it works great, and certainly worth a try, but don't expect miracles from it. So this is an example, and I'll just stop with this example because it says it all. Look at the prompt. Suppose the starting prompt is for multi-hop reasoning. Do you guys know what multi-hop reasoning is? Suppose a user asks a question. Where did the author of Mill on the Floss spend her early childhood, and how did the environment influence her novels? Okay? So you realize that this is not a question, it's a multi-hop question. Why? Because first you need to know who is the author of Mill on the Floss. That would be the first question. And let us say that you have created the first question and the LLM has responded. Or through RAG you have discovered, by search you have discovered that the author of Mill on the Floss is George Eliot. Right? The next question, what is the best next question? The best next question would be, where exactly describe in detail where did George Eliot spend her early years? Right? So this prompt is saying, produce the second query in a multi-hop. Right? Given a field question, so here is that compound multi-hop question. The question is the compound multi-hop question that cannot be answered just, for example, if you think RAG with just one RAG. Here is the answer to the first question. So this compound question has to be broken up into question one and then the rest, right? First question, Q1. So what would you do in a multi-hop question? You would give it to an LLM and you would say, give me the first question that must be asked. Do you see that, guys? In this case, the first question would be, who is the author of Mill on the Floss? So suppose you answer, so that would be in the summary. The author of Mill on the Floss is this. Now you can take the original multi-hop question and this extra bit of answer to formulate the next question. Are you getting it, guys? The next question is the query. So this is Q2. You're asking the prompt, an LLM, to produce Q2 in the multi-hop. So you realize that this is a very specific situation. If you give it a basic prompt that says, given the field's question, summary 1, produce the fields query. What would you say about this prompt? Would you agree that this is rather too brief and unclear, isn't it? So you give it to GEPA, and what GEPA does, it goes through generations after generations with GPT 4.1 mini, which is a relatively small model, and it comes up with this. You will be given 2 input. See, ultimately, it rewrites this prompt into this better prompt. You would all agree that this is a much better prompt. I'll just read the first few lines. You'll be given 2 input fields, question and summary. Your task, generate a new search query, optimize for the second hop of a multi-hop retrieval. The original user question is typically complex and requires information from multiple documents to answer. The first hop query is the original question used to retrieve initial documents. Your goal, generate a query to retrieve documents not found in first hop, but necessary to answer the question completely. Input understanding question is the original multi-hop question. Summary 1 is a concise summary of information from a document retrieved in the first hop, which partially addresses the question, purpose and context. So guys, do you notice that this query is beautifully written? Would you agree, guys, that if you had written it, would you rather have written the first query or the second query to create a good second prompt to get a good second multi-hop, to generate the second query in a multi-hop, guys? Anyone? Isn't it obvious?
That makes sense.
This is best, Yeah, nicely put.
Exactly. This is really the best. It has examples, it has everything that we have been talking about prompt, good prompting techniques. Everything is baked in here. And isn't it wonderful that you can start with something so vague a prompt as the first one, and through GEPA, you can discover this. Right? This is prompt optimization at its best. Right? And GEPA does discover. It takes time. By the way, I must also warn you, we have been doing this. While this is possible, it takes a few thousand, even if it takes a few thousand or a few hundred trials, you realize that those few hundred trials too, if you're using a frontier model like OpenAI, paid version, what does it mean? A few hundred or 1,000 calls to LLM. And before you know it, you get a bill for tokens. Right? So I would highly recommend that you do it with a free LLM, preferably with a local LLM. So we tried this internally with the GPT OSS 20 billion parameter. We also tried it with a few others, Quen and so forth. Right? So it does work. And does it lead to better results? So the rest of the paper is obvious, guys.
Hey, Asif, I have a quick question. Is multi-hop the same as prompt chaining?
No. Prompt chaining, yeah, in a way. There's some similarity. Multi-hop is a question that cannot be answered in one shot. Think RAG. Is there any document that will, or any chunk that will directly answer the question? Now, where did the author of Milan the Frost spend her early years, and how did the environment influence her later novels? It will be very hard to find such a chunk, isn't it? So you need to break it down to individual parts. Hop means chunk, parts. You need to plan out and do it piece by piece. That's what multi-hop is. So guys, this equation looks scary, but it is very straightforward. All it is saying is that, what is your goal? Expectation means over many trials, many examples. So let's go there. Over many examples. So this is the expectation value. When you see the expectation. Expectation is roughly average. Average over many examples. What are you saying? Taking this. Mu is, see, remember that the model is a function, given X, it's a function of two things, right? What is pi here? System prompt. And what is theta here? Params. Isn't that exactly what I have been saying? That this is a process of discovering. And mu is a measure of goodness, how good it is. It's a metric. How good is this? Right? And you're basically saying what I have been saying. This equation is basically what I have been saying. That, see, this is the equation, right? Given X, a system prompt, and a theta model, how do you go to the best output? And that best output is the journey that this prompt optimizer helps you take. Now, there's one figure that I would like to bring out. Where is that figure gone? No, it's way up here. Yeah, so here's the thing, guys. Look at this. This diagram is worth looking at. Suppose you have initialize it with some initial prompt, right? And you give it, you generate many candidate results, candidate variations of your system prompt. Then what you do is you have 3 tasks. Remember, we took the example, you have a task like how relevant is the answer, or on topic is the answer for a given question. Then second could be how well has it been answered, like how good is the grammar and style and diction, right? The third could be and so forth, like for example, how well argued it is and so forth. So let's say that this prompt P3 does task 1 well, P1 does task 2 well, and P2 does task 2 and task 3 well. But P0 and P4, they don't do any of the 3 tasks well, right? So what you do is you create your Pareto frontier out of only those prompts which did at least 1 task well. So that would mean for task 1, that would be P3. For task 2, it would be P1 and P2. And for task 3, it would be P2. So this is your Pareto frontier, right? So you have your Pareto frontier. Now what do? You take this Pareto frontier. You have a choice. You can take any one prompt, let's say P3, P2, and you can improve upon it. And then go through the process, right? Look at the trace, improve upon it. And then when you improve upon it, either it is good or bad. If it is good, add it to the next generation pool, right? Next generation candidate pool. And the other choice is that you take, and this is the genetic part of it, you take P2 and P3 and you hybridize them, merge them to produce another. This is a merge approach, and this is just a mutation reflective mutation. Yeah. So either of these two means randomly pick one strategy and apply it, and you will keep enriching the pool. After a little while, what happens as you go cycle through it again and again? So you keep cycling through it. And after a little while, your pool is really rich, and the prompts you're left with are much, much better than what you started with. So another way to think about it is that in the example of a candy, let's say, here is how I would say, let us say the prompt is, where did I? Where is my candy example gone? Yeah, so here is my candy example. So what is the Pareto a frontier decided by? It is decided by the budget that my parents would have given me for that fare to buy candies or to spend, right? So what would be the system prompt? Whatever I said to my parents to get that budget, isn't it? So suppose I prompted better, then what would happen? Then I could have a better Pareto frontier, isn't it? And a better budget, and a better budget, and a better budget, and that a Pareto frontier keeps. So what happens is that by better prompting, right, better convincing of my parents, I somehow am extracting a bigger budget, right, for candies. So that is literally what this paper is saying you're doing. You take candies on the Pareto frontier, but then what you do is you now think, okay, how could I have convinced my parents to give me a little bit bigger budget, right? And so on and so forth. So you are continuously pushing the Pareto frontier. And at the end of it, you end up with the Pareto frontier on which there are some really nice, juicy prompts, system prompt setting, very good quality system prompt setting. And that is the main idea of this paper. If you got that, you got this paper. The rest of it is, you can read it, you'll find it easy to read. After that, it's a long paper, it has a lot of examples in which it shows how it works, and many, many examples, and so on and so forth. But I suppose we have already exhausted by more than half an hour. So I'll take my questions and we'll end here. So guys, I hope it was fun for you to sit through this paper reading. It's certainly a very fun paper, and I enjoyed doing a paper reading on it. I hope you enjoyed listening to it, and hopefully the explanation was something that did help you a little bit. So, any questions, guys? Anybody has a question?
Yeah, Karthik, maybe you already answered, but one more time. So now that this technique is very useful to figure out even the model is not well responding to a domain specific question. Somehow using the GEPA, we can figure out best answer from that. Now, how do you figure out whether it's time for fine tuning versus keep trying with the GEPA? Now, what's a best practice? Yeah.
GEPA activates. After a little while, the GEPA program will finish. Okay. And what we found is GEPA also takes a long time. It took more couple of hours, but the improvements were real. And see, for me, that answer is very straightforward. And I keep going back to my escalation ladder. If you have to solve a very serious problem, why would you stop there? First is prompt engineering, then is prompt optimization, then any kind of sidecar I can bring, alternate models, tools, RAG, whatever else, and then finally go with fine tuning. Right? So I go depending on the seriousness of the problem, I keep going up the escalation ladder and ultimately see the real client or some real world will set the metrics. There's a threshold of acceptability. Right? Business will say that it must meet this bar. Wherever in the escalation ladder you start meeting that bar, you stop. Sometimes problems are simple, just simple prompt engineering will solve the problem. A large majority of problems is just basic prompt engineering. Right? Then, if it is not solved, then go prompt optimization or bring in sidecars like RAG, like tools, like this or that, alternate models, and so forth. Right? If that doesn't, agentic and all that, if that doesn't do it, now is the time to take off your gloves and get busy with fine tuning.
Yeah.
So that's what I do.
Okay. Yep. Thank you.
In favor of generating synthetic data.
Say that again.
Would you take this in favor of, like, say you have a fine tuning job that you need synthetic data on? Would you just go the GEPA route in that case?
No, you can use GEPA to create better synthetic data.
Oh, yeah.
To fine tune.
Yeah.
That's the way I would say it. All right, guys. Let me see if there's questions in the chat. So I hope you guys liked it, and I hope you guys like the this meetup series. How do you determine the concept of golden prompts for GEPA? No, golden prompts is exactly what you discover, Krishna. What you are saying is, no, not the golden prompt, golden answer. Sometimes what you do is, it's a form of supervised learning. You say that, hey, this is the input, and ideally I would have liked the output to be this. So then GEPA goes about thinking, what should I do to produce that? What is the best system prompt that I can do? And the best system prompt that it discovers is, I suppose, the golden prompt. The next question is, how do you compare and contrast GEPA and chain of thought? See, GEPA could be a chain of thought is a few examples. Like, for example, there's zero-shot chain of thought is simply saying, think step by step. But quite often you give a few examples. I would say that you start with whatever prompt you have with some chain of thought if you wish. GEPA will then enrich your chain of thought, add more examples, and make it better. GEPA is not an alternative to chain of thought. It will, where needed, introduce chain of thought into your prompt. And you can see that it starts introducing examples. Does that answer your question, Vishen?
Yes, I'd say it does.
All right, guys. So that's that. And I wish you all a very good evening. If there are no more
I
questions.
had another question real quick. Are there ever any instances where like GEPA ends up like contradicting itself within the prompt that it ends up producing?
I have not seen that.
Okay.
Because see, the pressure of trying to match the right answer usually is sufficient to prevent self-contradictions. But theoretically, it's possible. I just have not seen it.
Okay. But so you are kind of already giving what is kind of expected of a somewhat better answer, and then it's iterating towards that, and it can go past that, right? I'm guessing.
Yes, exactly.
Okay.
So what you do is, what happens is, I'll give you an example. Suppose there is I'll take a very simple example. There is something handwritten on the page, right? And there are a few numbers, there is some peculiar diagram. Now, system prompt may say, hey, figure it out. But the right answer should be, on the left-hand side is a logo of a company X, let's say support vectors. Handwritten, the handwriting to the left of it says this, and below it is the text blah. So that is the gold answer that you want. Trouble is, what is the system prompt you will give when you throw an image like this, let's say to a vision language model, right? You may just say, read what's on this image as a starting prompt. And as you may realize that might not give you as good an answer. So the process of GEPA or any prompt optimizer is a journey from there to say a better prompt, so that you will have an image, it can contain logos, and the logos may belong to companies A, B, C, or D, determine which of the 4 companies it belongs to. It is possible that you will get handwriting for the address, and the handwritten is the address, and at the bottom you may find further instructions, right? So now what has happened is you have come upon a much better prompt that the prompt optimizer may discover, and so the results that it comes up with is more aligned. Otherwise, what the VLU may do is miss some things, and that
Okay.
is it.
Yeah.
All right, guys, any more questions? Today is a fun day. We had a small audience.
I think Murali had a question. Can you talk about your experiments on GEPA and your learnings?
Oh, see, our experience, we have been playing with DSPY ever since it came out. We have, see, let us just say that it's a project with tremendous potential. Some of it is realized. Some of it is a lot work in progress. So that is why I put it in the escalation ladder. I don't say that DSPY will solve your problem. It sometimes solves it. It sometimes solves it completely and spectacularly. Quite often it improves upon it, right? By small amounts over your best prompt. And there are also situations we have seen where it made zero difference.
Okay.
And we got the only way, and those were mostly reasoning tasks, long, intricate reasoning or behavioral tasks. We noticed that there, prompt optimizers, including GEPA, doesn't help us at all. And for prompt optimizers, DSPY is our favorite library, and it doesn't help at all. Right? And in a more formal note, those people who are taking that agentic class will, of course, go through the lab exercises where you show you all these different scenarios. But this is a sort of a public forum. We're just walking through a paper. But we do have those, right? And one of the aims is developing a sort of a feel for when it will work very well and when it won't. You get that feel. I find that reasoning task doesn't do that well. It might sometimes take you a little bit further, but you need RL after that. You need fine tuning after that.
Does it this is like a bit of a weirder question, but would this like open up a whole mess of prompt optimization on your like gold standard itself? Because there's not an like explicit, I would say not loss, but explicit like gold answer, you could say, that's not determined by the LLM.
No, sometimes, see, if it is a verifiable answer, it's a math problem, then the answer is, gold answer is obvious.
Okay.
This is the target answer. You must get to it. So if it says that Mary started out with 20 apples, she ate 6, gave 4 to her neighbor, 2 rotted, how many is she left with? Suppose the answer comes out to be 2, but the LLM produces a trace of reasoning, and you tell it it's wrong, 20. So now what the LLM can do is it will reflect upon what went wrong, and therefore what it should do to the system prompt, how it should mutate it, isn't it? So, for example, it may just say, think step by step and make a table at each step, how many apples you are left with. That would be a very good system prompt statement to add, isn't it? And that to one question that somebody asked is literally introducing chain of thought as a method to better answer the question. And it will get able to do that. Any other questions, guys? All right, guys, I hope it was fun. So with those words, I'll conclude today's paper reading. Thank you again for being part of our Support Vectors Intel community, and I look forward to seeing you next week.